Okay, this talk is big data or fast data. Thank you all for coming. It's early in the morning for me. I'm Steve Millidge. I'm from the UK. I'm a director of a company called C2B2. So C2B2 are essentially a consultancy in the UK that are specialized in middleware, just middleware. So we're independent, so we do Red Hat, Oracle, VMware, open source. And what we really specialize in is non-functional aspects of middleware. So that is high availability, scalability, performance, reliability, and mainly on big scale systems. So from a big data, fast data experience, we've worked with, not me personally, but in our company, we've worked with Cassandra, Voldemort, HBase on the NoSQL side, and on the in-memory data grid side, we've worked in Coherence and InfiniSpan and Gemfire. So I have some experience in this area. I'm also on the JSL 107 caching API expert group, and the data grids one, which is actually not really doing anything at all at the moment. But so the point of this talk really is, first, I'm going to teach you all to suck eggs, as they say in the UK, which is I'm going to teach you, hopefully, principles of RASP. So that's reliability, availability, scalability, and performance. Go back to some first principles, and then look at what characteristics of NoSQL and in-memory data grids, that's IMDG, what they have in common. Because these technologies are very, very similar in their architecture. And we see, when we talk to customers, we see a lot of confusion about which technology to use for which use cases, because architecturally they are very, very similar. And we'll look at essentially the architectural aspects of these and many of their similarities. And then after that, we'll look at a few use cases and decide whether we should use a NoSQL store, big data, or in-memory data grids, which is fast data. So these big data, fast data tend to be marketing terms that are starting to get, well, big data has been used a long time, but fast data is getting used as a marketing term for in-memory data grids and stream processing. We won't talk about stream processing in this, just in-memory data grids. Okay. So, why do we as a company specialize in RASP? Well, essentially, if you don't have reliability, availability, scalability, performance, then you don't really have an application. Okay? What we see is many projects that we work on do agile development, which is a great thing, but agile tends to mean that many people forget about these areas of their system, and they're basically churning out functionality, sprint by sprint, and they forget about reliability, availability, scalability, and performance until a week before go live. But these are essentially priority one requirements. So we'll explore these a little bit. Reliability we're not really going to talk about too much. People confuse reliability with availability, essentially because they think of reliability in the same way as they have a car. It's reliable if it works. But that's not what reliability is in information systems. Reliability is essentially safety of your data in the case of a failure. Do you know the transaction model of your system? Do you know what happens to every piece of data if there's a failure? Is that data reliable? So imagine if you've got, you have one service calling another service. It's a synchronous call. What happens to your data if it fails halfway through that call, for instance? Do you resend? Do you not resend? These are all areas of reliability which take quite a lot of analysis to work out what happens in failures. And it's very, very important, obviously, because you don't want to lose any data, or you don't want data to be corrupted in the system. It should be in a level of consistency at all points in time. So essentially, reliability is about what happens in a failure. And we've had problems with customers. For example, one customer was taking bets and on a roulette, so it's essentially gaming, so it's a big system, many users. And someone had placed a bet on the roulette table, and according to his system, it came up as a win, but unfortunately, the system had crashed just at the point in time, or one of the back-end components had crashed just at the point in time where this person win, and they had no record of his transaction. And that caused legal challenge. The system is white-labeled to another third party. So knowing what happens at a system failure is very important. So availability is obviously known to all of us, okay? Availability is a system available for customers to use. Essentially, can you process some transactions? No availability obviously results in no transactions going through your system. Transactions equals pounds. P45 is a form you would get in the UK when you lose your job, basically, to tell you what tax you paid. So obviously, for many of us, availability is very important. And if you don't have availability as ops people or developers, then potentially you're going to lose your job. So it's different to reliability. For example, if you're going to had a car that was unreliable, one of the ways to get high availability, so the system can be used, is to have two cars, so that you can use a car when one of them crashes. So we're going to look a little bit into availability. You're probably all thinking, what's the point of this? But we're going to go into the architecture, a little bit of NoSQL, of how it solves some of these problems. So back to first principles and information in IT. So if you have three systems, system 1, 2, and 3, and to process a transaction, you must send data through all three systems in order for a transaction to complete synchronously, say. And each one of those systems is 99% available. Then your overall availability is basically you multiply the three percentages and you come out with 97%. Okay, now there's tried and tested ways how we increase availability. Essentially, there's effectively two different ways that you will increase availability in a system, and you'll do this without thinking as an architect. The first way is to create a redundant pair. Okay, so in a redundant pair, if each pair is 99%, if each node is 99%, then the pair total availability is calculated by that function. That gives you 4 nines availability. Okay, so if you take system 1, 2, and 3, pair them up, so each one now has 4 nines availability, then when you multiply those together, you'll get back to your original 99%. Okay? So 3 duplicate nodes will give you 99% availability again. That assumes, of course, that you've done your capacity planning correctly, and if one of those nodes fails, the other node can take over the load. Otherwise, you'll just get the second node failing. So for one of our customers, we did a capacity planning on a standard data grid. They had a 2-node cluster, which is not very big in these things, not really classified as a data grid. But when they did the calculations that when one of them failed, then essentially the JVM heap of the second one would fail. And essentially the system had no high availability, even though they'd clustered it, and therefore in their mind it was highly available. Okay, the other tried and tested technique is to decouple the systems. Okay, so in this case, system 1 will accept the transaction, so from the user's perspective, it has been processed, but it will asynchronously send it to system 2. And if system 2's down, it will store and forward and then push the data through the system when system 2 comes back. In that case, if you have 3 nodes, 99% available, then overall it's 99%. If you then double clustered those 2 up and paired them up, you would then get 4 nines availability. Okay, so decoupling is a technique that every architect will use, probably without thinking about why they're doing it, but it's to give you availability, assuming you don't code these systems badly so that you can't cope with failures. Okay, so when we go into customers, and we often look at deployments of this sort of software, and then you go to customer, and they have some really complicated way of starting the system up. It says, oh, system node, this system has to come up first before this system, because this system needs to connect to that system over JMS or something, and then basically what they've done is they can't cope with the unavailability of the first system. Okay, they don't reconnect, they don't check whether it's down. If it's down, then it'll reconnect periodically. If you do that, then you've essentially, even though you may have put async in there, you've broken your availability. So there's a standard theorem around this, which you may or may not have heard of, which is the CAP theorem. So this is a theorem of, I suppose, enterprise architecture, if you like. There's 3 system qualities. Consistency, which is essentially that all the system is in a total consistent state. So back to reliability, at all points in time, the system is consistent. You get one request, you'll get an answer. One question will always give you the same answer, no matter which component you talk to. That is consistency. There's availability, which is every operation must terminate in an intended response. So essentially, the system is available to process transactions. And there's partition tolerance. So this is the qualities of a large-scale, multi-node, distributed system. And partition tolerance is operations will complete even if individual components are unavailable. Okay? So what the CAP theorem says is there are 3 system qualities, but you can only have 2. You need to choose which 2 you have. Okay, so you can have consistency and availability, but if there's a partition, as in one node or one piece of the system dies, then the whole basically system has to stop processing. Okay, so basically operations will now be refused. And obviously, one that most people will choose is availability and partition tolerance. This is essentially the decoupling mode we have here. We said system 1 will accept requests, and it would store them up if system 2's down. So essentially what that means is you've relaxed your consistency, because if you query system 3, it's in a different state to system 1, to give you high availability and partition tolerance in that you can accept operations when a component of the system goes down. So let's have a quick look, go through performance. There's many ways that people talk about performance, but essentially performance is how fast does a single transaction take to execute. Obviously, we want performance because it involves happier customers. Sorry. And faster performance gives you more transactions on the same kit. And there's only a certain number of things. I mean, we do a lot of performance tuning as a company, and these are the only things that will kill your performance in an IT system. We've done many workshops, and no one has dreamt of anything else. Okay, so these are raw algorithmic performance, as in someone's written a bad algorithm, is very, very rare in a production system. Most developers are good enough to get that out of the system. You'll hit a resource limit, not enough CPU, disk, or memory. You will hit a resource contention, essentially locks, or you'll hit a latency, such as network or disk. And latency is essentially one of the key factors in large-scale distributed systems. So latency is defined as a time delay in requesting an operation and it being initiated. Okay, and latency is the one that is typically not taken into account by a developer in development. So latency is, it's the old, it was fast on my laptop type answer, but it's not fast when it's deployed on multiple data centers around the world. So the key factors when you're impacting latency are network distance. So if you have a data grid and a client to the data grid, sending a request on your laptop is going to be sub-millisecond. Sending it on the LAN might be a couple of milliseconds. Sending it across the WAN maybe tens to hundreds of milliseconds. So if it works on your laptop but the client's in New York and the data center's in London, then it's unlikely to be particularly quick. And that also relates to reliability. Network reliability, especially when you come to mobile, has a big impact. So you don't want mobile clients can be very unreliable and have very high latency. So you need to architect the system to not consume resources while a mobile client's accessing the system. And then you get into the interplay in latency between data size, operational granularity. Do you make one request for a megabyte of data or 10 requests for 100K of data? And that, again, will depend on your network distance and reliability. And then typical other latency factors are obviously resource contention, and in the Java world, JVM-GC. So, when someone comes to us and says they have a performance issue, the real question is, do they have a performance issue, a scalability issue, or a capacity issue? Because they are different things. Performance issue will go away if you throw more hardware at it, because it'll be algorithmic performance or something like that. A scalability issue is where throwing hardware at it may not solve the problem. Okay, so this would be like a resource contention, or latency or I/O contention. So we've seen systems where you throw more kit at it and the performance actually drops rather than improves, essentially because they slam it into the wall even faster. So scalability is the ability to add more hardware without a reduction in performance, hopefully an increase in performance. So horizontal scalability is basically adding additional servers, adding a load balancer, spread traffic across the servers, and that also gives you HA benefits by multiplying up the nodes that you have. This is essentially how data grids and NoSQL stores scale out. So what you're trying to achieve is the red line, which is linear scalability, add more nodes, process more traffic. And a typical scalability for a system is the blue curve, and what you'll be hitting is some sort of contention, which is throttling the system. In fact, most systems we know or go to see, most people don't actually know what the scalability curve of their system would be. Because actually producing a graph like that is actually quite a complicated thing to do. Well, it's not complicated, quite a time-consuming thing to do. Not a thing that a project manager is likely to give you budget for, to actually slowly test the system on one node, ramp it up, determine what the curve looks like against users, against throughput, then work out what limit you're hitting, tune the limit away, see what you can do, then add a second node, see what it looks like. I would say 90% of systems we go see, no one's ever done that, purely because of budget and time. But they all get the question of how many hardware nodes do I require to support X number of users? And most people will just put the finger in the air and say, ooh, 5. Okay? Or how much money have you got, and I'll buy that much kit. But it's something we would recommend you do, because it can be quite embarrassing when you throw more kit at it and you get absolutely no more performance. So, that's a quick wander down what is availability, scalability, performance. We will look at some of the architectures of data grids and NoSQL stores, which essentially follow these principles to give you big scale. And one of the things I would recommend is, before you decide you need an in-memory data grid or a NoSQL store, actually have a reason for doing it. We've seen many applications that, for example, will use HBase, and their data volumes are 100 gig. It's like completely pointless use of HBase, and massively complex architecture for no apparent gain. Similar with data grids. We've seen data grids with 2 nodes, which is pretty pointless as well. You may as well use application server clustering if you're going to do that level of grid. So I haven't got a slide that defines what these things are, so if you don't know what they are, an in-memory data grid is essentially a large cluster holding data in memory, and a NoSQL store, you'll see, is essentially a big key value store. So most of these things are key value stores. So a key value store is basically a big map or hash table, depending on your point of view. I would personally say they were a map because they have a key, as opposed to a hash, which is just a hash table. So most of them will have APIs where you put an object with a key and an object, some blob, and you get an object via a key. And these systems are essentially schemaless. In my view, the reason these things are key value stores is it relaxes a lot of the consistency problems that you would get on, say, a relation store, because you're decoupling their objects. So relaxing some consistency, you don't have foreign key rules that map across the keys, which need to be maintained. So it decouples schema objects. It also allows you to throw in any type of data because it's schemaless, and therefore obviously supports unstructured data. So the key can be whatever you want. So for example, we have an order against an order ID, a name for a person, postcode for an address, a content identifier for content or photo. Essentially, you have an identifier and some blob. Okay, so that gives us decoupling, relaxes some of the consistency, it allows us to build up availability. Okay, so the way these things scale is they essentially, given they're a big key value store, they just partition the key up. Okay, they split the key space, and they split that key space across multiple nodes. This is true of most NoSQL stores and most in-memory data grids. So this is common architecture. So, for example, they split into 4 storage nodes, for the sake of naming. They split the key space into a set of partitions for storage. Then when you put a key, so you put key B into the system, it will essentially store that in a single partition. Okay. Then when you get it, and you can get it from any node typically, and once you get it, the data grid or NoSQL store will know where the key is, and it will pull the key across the grid or set of nodes. It can be that you get intelligent clients that will know where the key is up front, so you won't necessarily have to hop across the storage. But even systems that support that will also support going to the wrong node and pulling the key across. Similarly, when you put an object into the grid or set of storage nodes, then it may actually live in a different node to the one that you access. But essentially, what you're doing is you're splitting the key space and storing objects in different nodes. So this is giving you scalability. The more nodes you add, the more storage you have available. And that's true, again, of NoSQL and in-memory data grids. They all have a set of storage nodes. They all partition the keys across a set of nodes. And each key will live in one node. Okay. Now, there's various ways that they do hashing to work out which node the key lives in. So there's consistent hashing, which is been around for a little while, which is the basis of Amazon Dynamo and Bigtable. So essentially, in this case, you take the key space, you split it up into a ring. The way you partition that ring between nodes is you hash each node, and that will give a node a position on the hash ring. And then that node manages all the keys between itself. So node 1 will manage keys between node 1 and node 4. Okay. The other way, sort of naive hashing that you could do would be to take the key, hash it, and do modulo against the number of nodes you have, and then work out which one to put it in based on the modulus. The problem with that is, if you add node 5, then you have to rehash the whole system. And what rehashing means, if you imagine these things are stored on disk, is that you'd have to move the whole lot of data around between the nodes. And if that's multi-terabyte, then that's going to take a hell of a long time. So the reason consistent hashing is called consistent is because the hash, you don't have to rehash the whole system, okay? Because basically the node picks a space in the ring, and it will manage things between it and the one below it, going clockwise. And then when you hash a key, essentially what you do is it has a space on the key, on the hash ring, like this red line, and you go clockwise until you find the node, the first node, and then that's the one that owns your key. Okay, so that's how they split it up. If you add a new node in, essentially, say you add a new node 5, which comes in here at that point, then it only has to talk to a couple of other nodes either side to start distributing keys. The rest of the key space is constant, and therefore you don't have to rehash the whole thing. Adding additional nodes is still expensive, depending on the size of the data, as you need to move it around between different nodes. But that's how you split the key space up. And splitting the key space up and partitioning the data gives you high availability. Sorry, it doesn't give you high availability, it gives you scalability. There's another way of doing this like many of the data grids use, and it's really for optimization, is that they don't have a hash ring. Actually, most of these are pluggable, so you could do it like that if you wanted. But what they do is key partitioning. So what they do is they assign a set of partitions, which is normally fixed, and normally a prime number for reasons I forget. And these partitions are then distributed between the nodes. And then when you get a key, its hash will put it in one of the partitions, and that will determine what node you have. where the number of partitions is always fixed. So if you add another node into the system, then it will just take ownership of a number of partitions. The reasons many data grids use this sort of technique is because there's a couple of reasons. One is they're optimized slightly differently. They're optimized for in-memory, and therefore what they want to do is redistribute it, so they're also optimized for more elasticity. So you often have nodes coming up and coming down in a in-memory data grid rather than more so than you would have in NoSQL. So when a node comes in, it just takes ownership of a number of partitions, and you can move whole partitions because it's a fixed size rather than a portion of a hash ring. So when something comes in, a new node comes in and takes ownership of a partition, it just copies the whole partition across. It doesn't have to work out boundaries between keys, etc. And another reason is most in-memory data grids will do something called key association. So you may hash keys, but you also may not. Because as we'll see later, for in-place processing, having related keys together is much more performant. So key partitioning gives us scalability, but it doesn't give us high availability. So, because if you lose a node of the partition, you've lost all that chunk of data. And that's typical of something like memcached, which uses a consistent ring, or memcached doesn't because it's dumb, but the clients will use a consistent hashing to work out which memcached server to put something on. But if you lose that server, you lose that area of the key space. So most systems will do HA key partitioning. So it's pretty simple. As we saw for HA, what you do is you duplicate things up. So in HA key partitioning, you have a primary partition or primary node in a consistent hashing scheme, and you have a backup. And you store 2 copies or X number or N copies of the data depending on your availability requirements. So in a consistent ring, you'll tend to pick the next node along as well as your backup. So you put it in the first node and then follow the ring round to the second node and put that as a backup. And in data grids, it'll tend to be a secondary partition. So basically, if a node crashes, you still have one of the nodes with the data. And when the cluster shrinks, the storage nodes shrink, then another node will come up as a backup, and the data will get moved around so that there's always n number of copies. So you may think this gives you, reduces your cap theorem because you need to increase consistency by having 2 copies. But there's normally optimizations in there that the second copy will be asynchronous and the system will become eventually consistent, as in eventually the second node will have a copy of the data. So if the secondary is down, then the primary will store them, or it will rehash depending on how you've configured the system, essentially, because rehashing is very expensive. If you're doing a rolling upgrade on one of these systems, you don't want to take a node down, everything to rehash, just to bring it back up again, and everything to rehash again. So it's typical to control when you rehash the data. So that's essentially how data grids and NoSQL stores work at a very high level. Why does this give us benefits? So a partition key space gives you, essentially, is linearly scalable. Okay? Because no matter how many nodes you have in the system, at worst case, you have 2 hops to read it, you arrive at a node that doesn't have the data, and the node that doesn't have the data fetches it from the node that does. Or if you use a client where consistent hash, you'll probably have one hop to the data. And similar for writes and updates. You will basically, worst case, you arrive on a node that isn't the one with the key hash, doesn't own that partition, and then the data will move across. Doesn't matter whether you have 10 nodes or 100 nodes, that's always the case. Okay, so the more nodes you add, it's linearly scalable. Performance should be constant. And also, the more nodes you add, the more data you can store. Because you're only storing X number of backups, then there's obviously more more storage space available the more nodes you add. And that's true whether it's in memory or on disk. The architecture is essentially highly available, as you can configure the number of duplicates. And it increases reliability because the system will eventually be consistent, and most of them have a concept of quorum, which is there must be X number of nodes available before it will allow data to accept data. So there's issues, performance issues with key partitioning architectures. And these are essentially, so imagine you have, a set of storage nodes, could be megabytes, gigabytes, terabytes of data, and you need to do some processing across that. So to do processing across that data, use a whole set of keys you want to process. So you need to go get on the keys. And what that will essentially do is drag that data off disk if it's NoSQL, and across the network if it's in memory data grid or NoSQL. So you drag in the keys across the network to process, and then any updates you do, you're pushing them all back. Okay, and this is where many people that use these products hit problems. Is that they want to process many keys in one transaction, in quotes, one business transaction. And they often, especially in data grids, they often hit network saturation pretty rapidly, and that tends to be the resource that they will hit and limit their scalability. So for in-memory data grids, there's the JSL 107 API, which is all get key-based, key value store-based access. And that fundamentally has a limit if you need to process a lot of data. And that limit's going to be your network bandwidth. So when you do large-scale coherence, if people are doing coherence as oracles in-memory data grid, people have to use 100 gigabit fiber essentially to get the network bandwidth. It will be a network bandwidth issue that kills their performance. So these products do what's called in-place processing. This can't be MapReduce, or in the case of data grids, it may be MapReduce or some other technique. But essentially, what you're doing is you're taking your processing, and instead of pulling the data across the network to the processing, you run the processing where the keys live. Okay, so you spread the processing across the storage nodes, you process the data locally, and then you bring your results back. Okay? In-memory data grids will support this. It may not be called MapReduce, and it probably isn't. It won't be MapReduce, but it's essentially the same thing. You send the processing across to the keys, and you process the keys locally. The reason you do that is the processing is probably much smaller amount of data than the data you want to process. So instead of dragging the data across the network, you send the processing across the network. And therefore, reduce the network bandwidth. It's only really, well, that's one reason to do it. The other reason is obviously you get parallelism. If you've got, so you basically use the whole cores on all the nodes. But if you're using a data grid, you may have to re-architect your whole application from using a normal caching, think of it as a cache with a cache API, to actually thinking it as a processing grid. So the first thing we tell people who start deploying data grid technologies is to forget about JSR 107 cache API, because that's not what you want to do. Because as soon as you do that, you're going to hit some limits. So, memcached, for example, you can only use a get and put API. But you may have the data cached, but you're going to have to pull it all across the network if there's a lot of processing to be done. So, being very simplistic, in-memory data grids and NoSQL stores architecturally tend to be very, very similar. They partition key spaces, they have map-reduce type capabilities, they use duplicates for high availability. The fundamental differences are, one, stored in memory, be simplistic, and the other is stored on disk. Okay, and that means in-memory data grids are essentially network products. They are optimized for network I/O. Okay, because all their communications is network. And they tend to be very clever about network issues like split brain or shunning nodes that are struggling. Whereas most NoSQL stores spend a lot of time optimizing for disk I/O. Okay? So the main question really is, which one of these is your problem? So the big question really is which to use when. So if we go into there's some terminology floating around at the moment called the 3 Vs for big data, which these are the 3 things that are changing that drive you towards big data. And these are velocity, which is how fast you need access. So we've got real time on the curve, near real time, periodic, and batch. And these are increasing in the sense that people want the data faster. And we've got volume, gigabytes, terabytes, petabytes. And then we've got different types of data. So, as in structured tables, databases, into photos, social, video, unstructured. And especially, effectively, the key factors in which technology you want is the volume and velocity. Except, as we'll see, if you're using huge blobs as at the end of your key, as in video, because you don't want to store video in memory. Okay, so if we look at volume, essentially, you're not going to get in-memory data grids that are going to scale out into the terabytes of memory. They're all, in theory, scale to terabytes of memory, but we don't see any in practice that are doing this. So this is where you're looking at using NoSQL stores, where you can use cheap disk to store on the storage nodes partitioned across. If you're in the 100 gigabytes and below, then you could look, sorry, not an in-memory DB, an in-memory data grid. So an in-memory data grid, if you think you've got 10 servers with 32 gig of RAM each, or 64 gig of RAM each, say 64 gig, that gives you 740 gig across the 10 servers, 640 gig across the 10 servers. If you put duplicates in that, so each piece of data has a duplicate, then in theory you've got 320 gig of memory to play with in an in-memory data grid. So they do scale up into the hundreds of gigs range when you partition the key space with a duplicate. However, if you're in the very, very high volumes, then you're really looking at NoSQL stores. So You could probably say to me that actually if you want to store the data, then you're looking at a NoSQL store. But the in-memory data grids tend to be very, very highly available. If you configure the duplicates, they can do rolling upgrades. So you don't, a lot of the cases, you don't have to actually store the stuff on disk. You can do them cross data center. You can push replicate across WAN if you really want to. So it is potentially, and people do this, run data grids without any database of record, if you like, behind them. Just running the data grid as the database of record. And that's particularly useful for, if you like, transient data in quotes that you would normally throw into a storage, such as web sessions, personalization, things like who's sitting on what table, gaming table in a gaming system, or state of transactions from a finance system for analysis. So it's not just, do I want to store this long term? I'll use a NoSQL store. It's really about volumes more than anything. And the other one is velocity. So the advantages that in-memory data grids have is they work at in-memory access speeds, okay, assuming your network's not saturated, especially if you're using the .MapReduce on them. So they can perfect for doing real-time, or probably not real-time in the strictest definition, but near real-time access to the data. So we're talking sub tens of milliseconds, which is not normally the space where the NoSQL stores will work, except maybe for single key access. So if you're in that sub 100 milliseconds, if the data needs to be processed and churned, say, within a user request, then you're probably in the in-memory data grid space. If it's batch, large-scale analytics, periodic access, processing huge data volumes, then you're probably more in the NoSQL store space. Okay. And then basically they're both key value stores. Both of them will support unstructured data. In-memory data grids just store Java objects. Whatever you want to put in a Java object, you can throw into a in-memory data grid, and you can throw into a NoSQL store. And effectively, the data size is a determinant. That's in the data size of a single key. If you're into large blobs like video, etc., you probably don't want to store those in JVM heap. It's not really going to help. So really big photos and video, etc., is probably best in NoSQL rather than in-memory data grid. So we're going to look at a few use cases and then look at where we see people using the different technologies. We do see a lot of people using the wrong technology for the wrong thing. And we see a lot of CV enhancing systems where people have used HBase to get it on their CV, but not for any architectural reason. Similarly for data grids. So if you have the scenario where you're accessing single keys, so a user, for example, wants to get, I don't know, a photo based on an identifier, so content management type use case. Or, say, a personalization use case where you have all users' details stored in a blob based on a single key. And or retrieval. I'll put EMD. Basically, in-memory data grids are typically faster. Okay? But most NoSQL stores are fast enough to do this sort of thing. So if you have huge volumes, put it in NoSQL. If you want to be ultra fast and you're in the 100 gigabytes, you put it in a data grid. Okay, so this is just where you're getting a single key. So in that scenario where that's predominantly your use case, I would say it depends on how much volume you've got and the size of the blobs that you're going to move around the network, which technology you use. If you think of Data grids, again, if it's too big, then it's best to stream it off the disk. So what about when your use case is to process multiple keys to give back a small result? So this is typical for things like financial risk calculations. So, for example, in a hedge fund, someone wants to place an order. They have to do a lot of checks to see whether that takes their holding in a company above a certain percentage, so they have to notify the authorities, whether it increases their risk profile too much. Lots and lots of different things. Essentially, you need to check a bunch of keys, process them, come up with a small answer, like, fine, book the order. And these will typically need to be done in sub 10 milliseconds, so that a trader can place an order. Similar for in the sort of sports betting market, where you're looking at someone placing a bet, and you need to check against their risk profile, have they gone past their limits, their wager limits, that sort of activity. And similarly, another area we've worked in the past is hotel availability. So someone wants to look at all the hotels in Paris for a certain date. You send the processing across the grid, check all the keys, and come back. So essentially, those keys that you need to look at may be hashed across multiple nodes. Okay, as we say, there's two ways to do that. One is you pull all the keys across the network to your application server or wherever you're running your logic. And because you don't know how big these are, that might be quite a large amount of data. And which means you may get affected by network latency. However, if you send the processing out to process those keys and come back, then that's much more efficient. So for these sort of use cases, that's where in-memory data grids tend to be much more better performant than NoSQL stores on their parallel processing. There's another reason why in-memory data grids are often quicker is because they don't all use consistent hashing, and they allow you to do something called key association, which is essentially take a piece of data that's related to another piece of data and make sure it's in the same partition, so that when you send the processing across, all the keys related to one key are likely to be on the same node. For example, if you have a user and much of the data with it, in most in-memory data grids, you can key associate the user's peripheral data with his primary key and ensure they're in the same partition. Much more difficult to do that in a consistent hashing scheme because you don't have partitions, if you like. But for when these things need to be done sub-millisecond in the user request cycle, these are probably best done in in-memory data grids. And we've seen financial trading applications get into sub 5-10 milliseconds by pushing all the data into a data grid, even when previously it was in NoSQL stores. There's another typical use case, which is write lots, read a little. So this is, one of them is like social media dumping, if you like, where people generate loads of crud in social media. Actually, hardly anyone ever looks at it, but you need to capture it all. That's one use case. The other one is log analysis, where there's vast quantities of log data getting generated, which at some point will need analysis, but most of the time it's never looked at. Another classic is SMS billing, where vast numbers of SMS events occur. People don't look at individual events, but for billing purposes, you need to count them up. Another area we've seen architecture like this is you're into cybersecurity or network security, so you're capturing packets, writing them away for future analysis. And this is one of the use cases that NoSQL stores like Cassandra and things are highly optimized for heavy write. Most of the in-memory data grids are highly optimized for heavy read and small write, because they evolved from caches. So if you have that use case, then you're probably better off using NoSQL stores. as they're optimized for that sort of scenario. Another one we see where these get used is essentially analytical intelligence. So this is where you are sending some processing across. You don't really care how long it takes, but you're sending processing across the network. It's chugging through vast quantities of data and updating another large quantity of data as it generates, say, summarization or new structures based on the analytics. Typical would be to take raw data like logs and process them to work out patterns and store more data back into the data store. So some of the use cases we've seen these is like consumer trend analysis, where you're taking clickstream information, processing it to work out which products the best people are looking at, which ones are getting purchased, how often they purchase it, once they've looked at it, etc. Or another one we've seen is route optimization in logistics. And these are obviously where MapReduce, Hadoop, and Extra have essentially come from, and this is they are the best technology for this sort of application. And what we have seen is where, I haven't got a slide, but where you have a NoSQL store behind a data grid. So the data grid writes through to the NoSQL store or reads through the NoSQL store. You do large-scale analytics on the NoSQL store, and you take the results of that analytics and push it into the data grid for essentially fast access for when the user comes on. So if you're going to take, say, recommendations, say you want to do large analytics on clickstream analysis of products, and you've captured all that in a NoSQL store to work out which product we should push at you next when you come on the website, then the analytics will be done in NoSQL. The product recommendations will be placed in a data grid so that when you come in and click on a web page, it can pull that data within your user request cycle, which typically most e-commerce will aim to get down to 100 milliseconds max. And then you pull that out of an in-memory data grid. Another one is real-time tipping. So it's just a term for it, but it's essentially where you are responding to events based on things that are occurring in the grid. And most in-memory data grids will have an eventing thing, which is probably pretty unique compared to NoSQL, which is essentially you can be notified as a client when a key changes or key is inserted into the grid. And this is used for recommendations, or we've seen it more getting hooked up with WebSockets. So for a use case like nudge purchasing, which is, say you're looking at an airline flight or a hotel room, and there's 6 other people looking at that hotel room. One way to make you purchase a transaction is to push to you that 4 people are also looking at this seat on the aeroplane, and there's only 3 available left at that price. Do you want to buy it? And those sort of things are done in in-memory data grids. So you track how many people are looking at the product. You can use the event capabilities. So when a key is inserted, it will fire off an event, and that can then be pushed through WebSockets. So data grids are good for that sort of use case. Oops. What happened there? Okay. So just to summarize, architecturally, these things are very, very similar. Partition key spaces, configured duplicates, in-place distributed processing, MapReduce, or something different, but essentially they're doing the same thing. So architecturally very similar. How they're optimized is different. So in-memory data grids are optimized for around the 10 to 100 gigabyte size. They are network products, so because they basically communicate via network. And they provide response times in the 10 to 100 millisecond So if you're in the user request processing, you're probably in an in-memory data grid use case, unless it's simple key access. And they can also provide push capabilities through eventing, through event models. The big data, you're normally in the 100 gigabyte to petabyte scale. If you're not in the hundreds of gigabytes to terabytes, then you probably don't need these products at all. You get away with MySQL, to be honest. The size is obviously limited by the disk. And these tend to be optimized for disk I/O. They are databases in that sense, so they spend their time optimizing disk I/O. Response times beyond getting a few keys, getting individual keys, will tend to be in hundreds to seconds. You can use them in line for small-scale key retrieval or small-scale processing. Okay. Any questions? Hang on, we need to use the microphone, apparently.
Hello. In the beginning, you talked about high availability techniques. The second of those was decoupling. And you said this would give you 99% availability because you would do the request asynchronously and just display the user that you did it. The problem is if this is a call that should retrieve data for the user to go on working on, this doesn't do anything for the user. You can display a spinning wheel 99% of the time, but it's not really available if you are dependent on the data of the dependent system.
No, but that means you've coupled all three systems. Therefore, you're not in the asynchronous. Architecturally, you haven't decoupled the systems. You may technologically, but architecturally, you haven't. If you need to go through all three systems to produce an identifier to give to a user. So it's an architectural issue you have.
Okay, thank you.
I mean, there are ways you could architect around that. You don't have to necessarily go to the third system to get the identifier. You could do it in the first one and do key mapping or something.
It doesn't have to be an identifier. It can also be, I don't know, policy data.
But I'll do a consultant answer. It's an architectural issue you have, and if you think of it as decoupling, you could architect it so you didn't need to go through three systems. Throwing JMS in it probably isn't going to solve your problem, if you do.
Okay, thank you.
For NoSQL solutions where you want to store data where the key sizes are pretty big, like say a megabyte or more, do you have any preferred solutions there? Because a lot of these NoSQL thingies don't work really well with larger values.
No. Nothing's going to work very. Problem with large key values is they take up large amounts of memory, and most of these systems will store these things in memory anyway to try and, optimize. Why would you need a large key?
Key values. Well, large
values.
Okay.
Sorry. No. Again, well, I mean, the ones that we see is often most people use HBase for that sort of stuff, and HDFS and things, because it's a bit more oriented around that. I mean, the ones we've seen for content management or for large scale, just dumping content will tend to be HBase. Whether it's better or the best, I'm not sure, but that's what I normally see. Okay, thank you very much.